The velocity of a wave is essentially a measure of how fast a wave is traveling. I already alluded to the fact that the speed of light in vacuum is a universal constant and a very special number in physics. The speed of light, the magnitude of its velocity in a medium will of course depend on the properties of the medium and particularly on an additional parameter which we call the refractive index of the medium, something you might already know. So, the velocity of the wave is a measure of how fast the wave is propagating, right. So, what about the prefix phase to it, the phase velocity of a wave, right. To be more technically accurate, for the co-sinusoidal waveform, the sinusoidal waveform that we have been considering so far, we can ask the question exactly what is propagating or moving, right. So, that is actually a somewhat intricate thing because this is a continuous phenomenon. A co-sinusoidal wave in its argument, that is cosine of kx minus omega t, can admit any value of x, positive, negative, going through 0, however large the value of x may be or t may be. Time of course flows just in one direction, so 0 onwards it increases linearly. It can admit any value of x or t, right, and the phenomenon is periodic in both variables x and t with periodicities of lambda and tau respectively, right. So, therefore, what is moving or propagating in this wave? And it is important to realize that what is moving in this wave is a particular point like the maximum or the positive maximum or the negative maximum or the zero crossing point. These points, it seems, are propagating or moving. In this case, where we describe the wave with cosine kx minus omega t, the wave propagates in the positive x direction or in the direction of increasing value of x, right. Had it been kx plus omega t, it would have been the other direction. To keep things consistent, let us take a forward propagating wave and discuss what happens there. Now, we can ask the question, that is, in what time did a point of a given phase, that is say a maximum, in what time did this maximum travel from a point x to a point with a spatial variable value of x plus lambda, right. Now, the answer to this question lies in the very definition of this sinusoidal wave itself. We told ourselves that essentially at every interval of lambda, the shape of the wave repeats itself, right, and this repetition in the shape happens after an interval of time tau, right. So, it is as if this point has moved from x to x plus lambda in a time t. It is as if this point, that is the maximum positive amplitude of the wave, has moved from a point x to x plus lambda in a time tau, right. Therefore, this phase point has moved x units in length after tau units in time. Therefore, the velocity with which this motion happens is essentially the ratio of the displacement divided by the time period, which is essentially lambda divided by tau. Since what moved is a phase point, that is a maximum, a positive maximum, a 0 or a negative maximum or any such intermediate point, this quantity is called the phase velocity of the wave. Now, it is with some foresight that we ascribe the adjective phase to velocity. If we describe the motion of a particle in physics or engineering, we simply use the term velocity. We do not quite often bother to ascribe adjectives like phase velocity or whatever else. In the case of waves, this becomes important because we will very soon consider phenomena where we do not have just one sinusoidal wave, but a collection or a group of sinusoidal waves which can propagate together, much as we see in possibly day-to-day scenarios. A group of birds, a group of starlings, for example, fly together and form a shape, for example. And it's a very nice example because such a apart from being an aesthetic observation, it's a very interesting phenomenon in physics too, because it's a group of objects which are flying or propagating and could also be described by wave-like phenomena in their dynamics. But coming back to the point we are discussing here, a group of cosinusoidal waves, for example, with different wavelengths, values for the wavelength or frequency, could also co-propagate in a medium, and we will prove that to ourselves in a somewhat rigorous way, that they can co-propagate in a medium without sort of disturbing or touching each other, to put it somewhat loosely but effectively. When we describe groups of waves, then a different form of wave velocity will also need to be defined in order to describe the physics. In the case, therefore, of a wave with a single value of k and omega, it is very apt to use this value of velocity or this parameter called the phase velocity, which is the ratio of the wavelength to the period of this wave, right. Now, we can also use the notion of frequency, which we have just developed from the temporal periodicity of the wave, that is nu, which is equal to 1 over tau. So, that V simply turns out to be the product of wavelength, which is spatial periodicity, and nu, which is the temporal frequency. Okay. So, we can write therefore down the magnitude of the velocity of the wave as omega by k, here substituting for lambda to be lambda is equal to 2 pi divided by k, or nu to be equal to 2 pi times omega. Okay. So, let us take a pause here. We have been describing things for quite a while now. If you are watching this video, as the case may be, on a platform like the NPTEL platform or YouTube, please pause your video on the next view graph, and let us check and test our understanding of waves using a slightly unusual scenario. Ready? As I said, waves can essentially be formed out of any kind of physical objects. It could be a group of birds flying, or in this case we describe a somewhat popular scenario. So, this is a stadium, a sports stadium. So, it could be a football stadium, or a stadium where the game of cricket is played, or something like that, or baseball, whatever your favorite game is. One often sees in these stadia very motivated or inspired fans doing what we are describing in this picture here. They get up and sit down from their seats in the stadium to form a wave, which sometimes is called a Mexican wave in certain contexts, but it is a human wave. So, this sort of uprising and falling, or the standing up and sitting down motion, is also it turns out to be periodic. Although this is not really an idealist wave of the kind that we have been talking about, it is still a propagating phenomenon. So, even for a phenomenon like this, we can ascribe a spatial periodicity. That spatial periodicity is typically tens of seats. So, let us say the spatial period of the wave is 20 seats, and the temporal period of this wave, the period after which successive people get up and sit down, is about 1 second. So, tau is replaced here by capital T for the time period, it is 1 second. So, the question is, take 10 seconds and calculate the phase velocity of this wave. Are you ready? So, please go ahead and calculate the phase velocity of this wave. I will give you the answer after 10 seconds. If you are watching this on video, please pause this video at the moment. Okay, now I hope you had enough time to make this simple calculation. What did we have as the expression for the phase velocity? The expression we had is v is equal to lambda divided by t in this case. So, lambda is 20 seats, seats is the unit of length here, divided by 1 second. So, therefore, the phase velocity of the wave is 20 seats per second. Okay, 20 seats per second is the phase velocity of the human wave. It is just as accurate and just as fine to describe these waves also as these phenomena also as waves. Let us resume after the question pause. We have been dealing with this form of the mathematical description of the one-dimensional light wave, where we care so far only to use the electric field as a function of space and time to describe the wave propagation. X is the spatial variable, t is time, and we said that the most fundamental solution is a sinusoidal function. We have referenced ourselves to the cosine. So, A, the constant amplitude multiplying cosine of the argument which we earlier wrote down as kx minus omega t minus the initial phase or absolute phase theta, right. So, now since cosine is a trigonometric function, the argument to the trigonometric function is a phase, it is an angle, right. The phase clock ticks all the way from 0 to 2 pi and repeats itself and goes on sort of wrapping around in periods of 2 pi, which is the periodicity of this trigonometric function, right. So, this entire phase factor phi, which is, we should observe right away here, a function linear in x and linear in t, can be considered in a more generalized scenario to be phi a function of x and t. Okay, this phi is not a constant like theta. Theta is independent of x or t at the moment. Okay, so phi is the phase of a wave. The phase is everything inside the cosine here. Okay, now let's just keep to this definition of the phase function phi. So, this is a definition for the phase function. It's phi is a function of x and t. If we take to this rigorously, then we can now squeeze out omega, the factor here, to be the partial derivative of the phase function phi with respect to t with a minus sign prefixed to it, and the constant k, the magnitude of the k vector, the wave vector, to be the partial derivative of phi with respect to the spatial variable x. Okay, so this is more or less obvious if we look at the function phi, which in this case, in the case of the simplest wave that we have considered, is kx minus omega t minus the theta. Okay, so these are results we can prove more rigorously later during the course as needed. If we take this account to be what it is, then the velocity of this cosinusoidal wave is essentially the ratio of omega and k. V was omega by k, therefore V is equal to this partial derivative, which is minus d phi by dt, divided by the second partial derivative with respect to the spatial variable x, which is d phi by dx. Okay, so this velocity, in the sense of the definition of the phase of the wave being phi of xt as function of space and time, gets defined to be the ratio of two derivatives minus d phi by dt divided by d phi by dx, which are both partial derivatives with respect to the variable of interest t or x respectively. Now this formula is useful in contexts where, like what I alluded to earlier, a group of simple cosinusoidal waves, which are in some sense pure sine waves, propagate together. For those of you who are advanced learners in this course, you can possibly catch what I'm hinting at: wave groups, decomposition of more complex waves in terms of sinusoidal waves, and so on and so forth. In all such scenarios, this velocity essentially becomes a very pertinent quantity. Note also that we have generalized the notion of the phase velocity, which is a very appropriately defined physical quantity relevant to the case of a pure sinusoidal wave described by three constant quantities, that is k, omega and theta, right, which assume unique values in this case, unique fixed constant values independent of x or t in this case. For this particular scenario, v is the phase velocity. However, if we had any other feature in the wave present, which aptly will be captured by the phase function phi of xt, then this quantity v need not be the phase velocity. In the case of the simplest ideal, what we would call monochromatic infinite sinusoidal wave, this ratio of minus d phi by dt divided by plus d phi by dx turns out to be the phase velocity. Now we can we are in a position to appreciate another interesting or important quantity, which is a phase delay. Generally, in our day-to-day notion of delay, we would have come across this term delay in the context of time, delays in time. One would possibly say that the flight was on time, my flight was delayed, my train took off on time, it was delayed. It rarely is early, isn't it? Or I'm early to the class, I'm delayed in arriving to the class, or so on and so forth, right? So delay is a conceptual notion associated with time. So let's define delay in the context of a wave. Let's delay something in the wave by a unit of time. Let's call the delay to be t in units of seconds, which is the standard unit. So it's helpful to define this delay by an amount t that the wave experiences after propagating a distance d. This scenario is essentially sketched in the view graph, the plot on the top right corner here. So we consider an instant in time and let the wave propagate for a duration t, and we will now look at what happens or what is the state of this piece of the wave after it has traveled a certain distance d in a time t. Okay, so that's what the animation shows here. So in a time t, the wave travels a distance d. All right. So now we can write down this time delay in terms of two quantities. One, the distance d that was traveled by any phase point. Let's pick, say, this maximum. This maximum has traveled from this location x all the way to this location x, which are separated apart by d units in space. Right? So now we have, and this process has taken a time t. So therefore, this point has moved from its initial location. This maximum point has moved from its initial location. Repeat. This phase point has moved from its initial location here in time t to a later location that is separated by a distance d away from the initial location. That is here. Right? So, given the fact that the wave propagates with a constant velocity, we can relate t and d by t is equal to d by v. Okay. So now this time can also be expressed in terms of a phase delay phi. We are using two different phi's in this discussion, so please note and be careful. So there is the phase delay phi written with a long stem, whereas phi of xt is just written with a tail. So there are two different phi's. It just so happens that physicists and engineers tend to like using phi and theta for phase, these Greek symbols, and use the multiple ways in which it's written so that we keep the notation somewhat compact. So please bear with us and do not get confused. So the phase delay phi is essentially computed this way. So take the spatiotemporal phase factor phi of xt, compute phi of xt at the spatial location x plus d at time t minus phi at the spatial location x and again at time t. So now these two are phase quantities, so they can take values between 0 and 2 pi or even larger values, in which case it would be argument of a periodic function anyway. So this quantity, so phi of x plus d of t, essentially for the cosinusoidal wave that we have been considering so far is k of x plus d minus omega t minus theta, the initial phase, minus phi of xt, it is kx minus omega t minus again the same initial phase theta. So therefore, the phase delay phi, computing this, turns out to be essentially a very simple quantity. All we need to do is to cancel out the two kx's, to cancel out the two omega t's from this distance and cancel out the two thetas from this difference, and what we are left with would be just the factor kd. So the phase delay is essentially phi is equal to kd, but then we can now use the relation that we just alluded to a little earlier, that is t is equal to d divided by v, right? So substitute for d over here, so d would essentially turn out to be v multiplying t, and then we use the fact that v is equal to omega by k, and therefore the phase delay, which is again in radians, is either kd or omega t, right? So this is again something we will use later in the context of, say, interferometers, interferometry, and so on and so forth. But the concept of a phase delay is very much an important facet of optics. So we can see that this is associated with two other notions or concepts. One is a time delay as well as a spatial offset, which is d. And we have sort of two equivalent descriptions: a spatial offset or a spatial displacement d, or a delay in time, which is t. Both of which are once again going to appear and manifest themselves in our discussion of attosecond physics.